Okay, so in my ISN, I actually went ahead and cut up my foldable into 3 pieces, and I'm going to do my 3 examples by them. In your ISN, you can do whatever you want. You can just glue in that one piece over here and do 3 examples, but I want mine kind of divided up so I can see what example goes with what. So let's start with another eliminating the parameter basic problem. So say our 2 parametric equations are x equals t minus 2 and y equals t squared. We're going to solve one for t, just like we did in our foldable. And I'm going to solve this one. It looks pretty easy. So I'm going to add 2 to the other side, and I get t equals x plus 2. And now I substitute. So I'm going to have y equals, but instead of t squared, I'm going to have x plus 2 squared. And I just square that, double distribute it out, and I get x squared plus 4x plus 4. If you're interested in how I did that so quickly in my head, you can talk to me about it during class or ask then. And there's no restrictions here because with this equation, x could be anything, and with this equation, well, it doesn't really matter what y can be because y is dependent upon x here. So that really isn't a factor. We just have to look at x and check the domain. So let's go to our next example where we might have a restricted domain. Hint, hint. And let's do the equations x equals the square root of t plus 2 and y equals t minus 1. Okay, so we can see here that they're squared. We could do this one, we could do that one. Typically, we actually like to try to isolate t in this equation just because most equations in mathematics are y equals. So I'm actually going to square both sides of this just like we did in our example over here to get t by itself. So I'm going to square both sides and I get x squared equals t plus 2. And then subtract 2 on both sides and I end up with t equals x squared minus 2. So from here to here to here. Now we lost something when we did that though. When you square this, you take away the fact that t could only have been certain values. Okay, t could only have been -2 and up, which really limits what x could be. So x could only be 0 and positive numbers. So we need to note that restriction on the domain. So we'll do that whenever we write our final answer. So now we're going to plug this in where t is at, and we end up with y equals x squared minus 2 minus 1. And of course these two constants are like terms, so we're going to say y equals x squared minus 3 such that x is greater than or equal to 0. So no negative numbers are involved. And again, if we plug that in our graphing calculator as a coordinate grid equation, we'd have x squared minus 3. And it would graph a parabola, but with the parametric equations, this whole left side would be gone. Let me even prove it to you. Let's do some parametric equations. So let's do our originals. Square root of t plus 2, and our second one was t minus 1. So if we graph it, well, that didn't work out, now did it? They're supposed to be the same. That is troubling and very strange. Well, that's something for me to ponder on and figure out. But in the meantime, let's move on to the last example. Eliminating the parameter with trig identities. So here we're going to have, and I'm going to write this down below because it's kind of a longer problem. X equals 2 plus 4 cosine of t. And the second one is y equals negative 1 plus 3 sine of t. And here they give us a restriction on t. They say that t is going to be greater than or equal to 0, but less than or equal to pi. So we can't just look at the amplitude to tell what the limitations on x are going to be. We have to realize that only half a period is going to be completed here. So we have to really think about that whenever it comes to this trig equation at the end. But in the meantime, let's go ahead and go through our process. We're going to solve for the trig functions. We can't get t by itself. Using the inverse would not be helpful here. So if you were wondering about that, it doesn't get us anywhere. So instead, we're going to get cosine by itself. So for this equation, we're going to have x minus 2 equals 4 cosine of t. We've got to get rid of constants first. And then we're going to divide both sides by 4 and get x minus 2 over 4 equals cosine of t. Now we do the same for y. We're going to have y plus 1 equals 3 sine of t, and then divide both sides by 3 and get y plus 1 over 3 equals sine of t. Now at this point, we've got a cosine and a sine equation. If we square them and then add the lefts and the rights together, then we'll have something we can use the Pythagorean identity on. So let's go ahead and do that. We're going to square the left and the right. And so this is going to become x minus 2 squared over 16 equals cosine squared t. And this one's going to become y plus 1 squared over 9 equals sine squared t. Now before you start double distributing this out, don't do it. Because what we're actually going to be creating is a special kind of equation. So we don't need to double distribute whenever you're doing these trig parametric equations. And so now we bring them together, and we're going to have x minus 2 squared over 16 plus y minus plus 1 squared over 9 equals, so that's our left sides added together. And then our right sides are going to be sine squared t plus cosine squared t. And just to make it clear, I'm going to kind of do a little highlighting here to show that we added the two equations together. And then at this point, we know that all this equals 1, so our final answer is x minus 2 squared over 16 plus y plus 1 squared over 9 equals 1. And this is a special kind of equation that I wish we would have had time to look at last year. It's actually called a ellipse. Okay, so I can't show you what it looks like while it's in this form, because it's not a y equals equation. And that's another reason why parametric equations are so useful. I can go in and type these and show you what it looks like. So 2 plus 4 cosine of x or t. And then here we've got negative 1 plus 3 sine of t. And I have to change my mode to radians. And then graph it. And you can see it's like an oval. So the math word for that is an ellipse. And you might see these types of equations somewhere on the ACT. And just a little bit of info on it. Well, no, I'm not even going to go there. Okay, so anyways, yay for you. Now you know about ellipses. But the last thing we have to do is talk about the restrictions. Okay, so because we're only going to be in the first and second quadrants between 0 and pi, we have to think about that. Now with cosine, we know that it starts at 1 and it dips down to negative 1. by the time it gets to 180. So cosine is going to have all the values between its highest point and its lowest point. So it's going to be x is greater than or equal to -2 all the way up to 6, because you've got your vertical shift plus your amplitude and minus your amplitude, and that gives you the two values that it oscillates between. But sine, on the other hand, when you think about it going to 180, it only does the positive values from 0 up to 1. So here it's going to go from its vertical shift, which is -1, up 3, but those are the only values that it's going to use. So we have to say the restriction on the y values is from -1 up to +2. Now, a couple of questions. You may be wondering, why did we find the restriction for x and y on this problem? Because of the way it's set up. It isn't y is dependent on x. They're both dependent on one another. Whereas in this last example, y is dependent on x. So the only thing you need to worry about is the domain. In this example, it's just not the same. So if that's something you're really curious about, we can hash that out in class as well.